Hello, class. This is part 3 of our section 1.8. To continue on with these continuous functions, we have composite functions. So if you recall from algebra, composite functions, this is where we have f of g of x, this being f of g of x. If f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is f of b, or we could write it as the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. And likewise from that, if g is continuous at a and f is continuous at g of a, then the composite function f of g can be given by f of g of x is equal to f of g of x, and that being continuous at that value of a. So then what does that mean in terms of a couple of examples where we want to see whether these functions are continuous or not? H of x here is equal to the sine of x squared. So we could break this up, right? G of x is x squared, that being a polynomial, continuous everywhere. F of x is equal to sine of x. Again, trigonometric function, so continuous everywhere. Both of these are continuous everywhere. So this particular composition, this being f of g of x, this is continuous on those real numbers. For capital F of x is equal to 1 divided by the square root of x squared plus 7 minus 4. So we could kind of break this up, right, into multiple functions. We could let lowercase f of x be 1 over x, g of x being x minus 4, h of x being the square root of x, and k of x being x squared plus 7. So because of this, right, we have a couple of things to make note. But due to this being a rational function, we need to look at that domain to find where it cannot be, where it cannot exist for this. So we have all the values of x that are real numbers, such that the square root of x squared plus 7, this cannot be 4, due to this square root of x squared plus 7 minus 4 in the denominator. So because of that, this happens of all the values of x such that x cannot be positive or negative 3. So in terms of what that means, this occurs then that we are continuous on the following intervals. That being negative infinity to negative 3, union negative 3 to positive 3, union 3 to infinity, since we are writing these as sets. That is part 3 of this section 1.8. Be on the lookout for part 4.